In this installment, we'll talk about how to make tertiary alcohols using Grignard reactions. This is going to be one of the most important reactions that we learn because we're going to start making carbon-carbon bonds and start building more complex molecules from relatively simple starting materials. So in the previous video, we talked about how you can make primary and secondary alcohols using reduction of a ketone. So in this video, what I want to talk about is how would we make a tertiary alcohol? If we think about this backwards, right? If we wanted to make this from a ketone, we would need to make a new carbon-carbon bond, right? What we would need to do is either form this bond or this bond or this bond. How would we do that? Well, let's think about this. If we have 3-pentanone, if we wanted to make a secondary alcohol, what we did was sodium borohydride was a negatively charged hydrogen that added to this carbon, breaking the pi bond and forming this new CH bond here, right? So if we wanted to do something similar, right, what we need is a new CH3. So we need a CH3 minus, something like a CH3 minus that could add here. That would give us a new carbon-carbon bond and result in a tertiary alcohol. So what we're going to talk about in this video is how do we make carbons with a negative charge. And the way that we do that is with magnesium metal. So if we take magnesium metal, add it to an alkyl halide. So let's say we take butyl bromide, we react it with magnesium metal. The magnesium actually inserts in between the carbon and the bromine. We get this species, which is called a Grignard reagent. If you look at the periodic table, right, magnesium is on the far left side of the periodic table or pretty close to it. So magnesium is not very electronegative. So the result actually is a negatively charged or partially negatively charged carbon, because carbon is much more electronegative than magnesium is. And so now what we've done is we've turned carbon into a good nucleophile. The way that a good shorthand for thinking about Grignard reagents is just like I mentioned, this carbon is going to be partially negative, the magnesium is going to be partially positive. The way you want to think about this, though, is like the example that I used on the previous slide. You have a lone pair of electrons on the carbon, so you want to think about this almost like a carbanion with a magnesium bromide plus counterion. So this is going to act as a nucleophile with a lone pair of electrons with a carbon attached to a carbon. This is what we're going to use to make new carbon-carbon bonds and build up complexity in organic molecules. Okay, there's other kinds of organometallics and there's other ways to form Grignard reagents. So for halogens, we could have a chlorine or a bromine or an iodine here. We add magnesium, we're going to get a Grignard reagent. If we start with the same kind of species but we add 2 equivalents of lithium metal, we're going to get an organolithium reagent plus lithium chloride or lithium bromide or lithium iodide. This, again, you want to think about as sort of a carbanion with a lithium counterion. So these things are kind of written interchangeably. You can write this as an ionic salt, or you can write this as a covalent bond between carbon and lithium, where the carbon has a partial negative charge. I've seen it written both ways, and both are useful for different reasons. Okay, so if we take, for example, let's say that we go back to the example that I gave earlier. We take 3-pentanone and we react it with methyl magnesium bromide, which we can represent as CH3 minus and an MgBr plus. CH3 minus is going to attack the carbon and break the carbon-oxygen double bond. So this should look familiar because very similar to the mechanism of a reduction, right? If we have borohydride, the hydrogen is partially negatively charged, and that's going to be attracted to that partially positively charged carbon. We can also, so let me just, before I get ahead of myself here, we'll get something that looks like this with an O minus. And then in a second step, we'll add water to protonate that alkoxide to give us our final alcohol product. So actually, I'll draw it like this. Right. The other option would be to draw the mechanism like so, which is kind of more similar to what we showed for sodium borohydride. If we have carbon magnesium bond, if we draw this as a covalent bond, we can just draw the bond attacking the carbon, and we still get a new CH3 and an O minus here. Either one is correct, but notice that no matter what, if we take a ketone with any Grignard reagent, we can get whatever tertiary alcohol that we want. We've made a new carbon-carbon bond, which is really important if we're talking about organic molecules that are composed of carbon. Forming carbon-carbon bonds is pretty important. Okay, so for example, we could start with a ketone, like cyclohexanone, treat it with methyl magnesium bromide, followed by water. Water is what sticks on this hydrogen, and we formed a new carbon-carbon bond. So ketone plus Grignard gives us a tertiary alcohol. Aldehyde plus Grignard gives us a new secondary alcohol, and we've formed this carbon-carbon bond in the product. What if you have an ester? Esters react with excess magnesium, excess Grignard reagents to give tertiary alcohols. Notice that the methyl added twice to this carbon. Why is that? Well, let's think about the mechanism here. So you have CH3MgBr. This is an electrophilic carbon. So we attack that, we break the pi bond. We have an O minus here. We have an O methyl here. We have a CH3 here. What can happen actually is that we can reform the pi bond and kick out methoxide, which gives us a ketone. And we already know that ketones can react with Grignard reagents again. So a second CH3 can add to that ketone, which would give us two CH3s. So you want to look out for this. If you see an ester reacting with a Grignard reagent, you want to make sure that that Grignard is going to add twice to your ester to give you your tertiary alcohol product. Another thing that you want to look out for is the fact that Grignard reagents are extremely strong bases, which makes sense, right? So let's think about a specific example like methyl Grignard. If this reacted with any source of a proton, right? So if we think about this as a negative charge on carbon, this hydrogen is partially positively charged. So if we pull that off, what do we get? Well, we get methane plus hydroxide, right? And methane is a much weaker acid than water is, a difference of 32 pKa units, right? So this equilibrium is going to lie all the way on the product side. So you want to avoid any acidic hydrogens that whenever you're working with Grignard reagents, you must always avoid acidic hydrogens. So the take-home message here is Grignard reagents are not compatible with water, with alcohols, with amines, with carboxylic acids. Anything that possesses an acidic hydrogen, an OH or an NH, is not going to be compatible with a Grignard reagent, because a Grignard reagent is just going to act like a base faster than it will act like a nucleophile. So for example, let's say that we wanted to form this Grignard reagent. It's impossible, because this strong base is going to immediately react with the OH that's in the same molecule. So you cannot form Grignard reagents from molecules that have other acidic functional groups, even weak acids. Okay? So how do we get around this problem? What if we want to make this particular Grignard reagent or a product from it? Well, what we do is we use protecting groups, which I'm going to talk about in a second. So if we can take this OH group, mask it as a protecting group, then we don't have an acidic hydrogen anymore. We can turn that into a Grignard reagent and react that with a ketone to form this bond, and then we can remove the Grignard reagent to get our OH group back. The best protecting group is, or the one at least that we're going to talk about, is trimethyl silyl group. So we have a silicon bonded to 3 methyls. If you react that with an alcohol, you get a silyl ether. Notice that we don't have that acidic hydrogen on our alcohol anymore. This is often abbreviated TMS for trimethyl-silyl. So you can take an alcohol with TMS chloride and form a silyl ether. Now we don't have that acidic hydrogen, that alcohol is protected, and we can carry it through the synthesis. And then if you want to remove silicon, you can add a source of fluoride, which fluoride has a high affinity for silicon, and we get back our alcohol. Let's see an example of this on the next slide. Okay, so let's say we take the same alcohol that we had on the previous slide, but instead of making the Grignard reagent right away, react this with trimethyl chloride and an amine base, triethylamine. Now we formed our silyl ether, right? We don't have our hydrogen on there anymore. So now we can treat this bromide with magnesium without having to worry about those competitive acid-base reactions. Then the Grignard reagent is going to attack our carbonyl compound to form an alcohol when we protonate with water. And then TBAF is tetrabutyl ammonium fluoride. So it's just tetrabutyl 4 butyls on a nitrogen, and the counter ion is fluoride. So this is just an organic soluble source of fluoride, which removes our protecting group to give us back our alcohol. So this is how you're going to use protecting groups. Okay, so to summarize and to boil this down to the important points here, you're going to form Grignard reagents, which are nucleophilic sources of carbon, by treating alkyl halides, chlorides, bromides, and iodides with magnesium metal. They're nucleophilic because now carbon is more electronegative than the metal, and so it has a partial negative charge. You can use Grignards with aldehydes to give secondary alcohols. You can react Grignards with ketones to give tertiary alcohols. And then I want you to understand how and why protecting groups are used to avoid these competitive acid-base reactions that we just talked about.